In this presentation, I'll go through some notes from Chapter 4 of the book, Designing Data-Intensive Applications. Chapter 4 is called Encoding and Evolution. This chapter looked at various ways of turning data structures into bytes on the network or bytes on disk. We saw how the details of these encodings affect not only their efficiency, but more importantly, also the architecture of applications and options for deploying them. In particular, many services needs to support rolling upgrades, where a new version of a service is gradually deployed to a few nodes at a time, rather than deploying to all nodes simultaneously. Rolling upgrades allow new versions of a service to be released without downtime, thus encouraging frequent small releases over rare big releases, and make deployments less risky. That is, allowing faulty releases to be detected and rolled back before they affect a large number of users. These properties are hugely beneficial for evolvability, the ease of making changes to an application. During rolling upgrades, or for various other reasons, we must assume that different nodes are running different versions of our application's code. Thus, it is important that all data flowing around the system is encoded in a way that provides backward compatibility. That is, the new code can read old data, and forward compatibility. That means old code can understand new data. Chapter discussed several data encodings formats and their compatibility properties. For example, programming languages, specific encodings are restricted to a single programming language and often fail to provide forward and backward compatibility. Texture formats like JSON, XML, CSV are widespread, and their compatibility depends on how you use them. They have optional schema languages, which are sometimes helpful and sometimes a hindrance. These formats are somewhat vague about data types, so you have to be careful with things like numbers and binary strings. Binary schema-driven formats like thrift, protocol buffers, and Avro allow compact, efficient encoding with clearly defined forward and backward compatibility semantics. The schemas can be useful for documentation and code generation in statically typed languages. However, they have the downside that data needs to be decoded before it is human readable. Chapter also discussed several modes of data flow, illustrating different scenarios in which data encodings are important. Databases, where processes writing to the database encodes the data and the process reading from the database decodes it. RPC and REST APIs, where the client encodes a request and the server decodes the request and then encodes a response and the client finally decodes the response. Then we have asynchronous message passing using message brokers or actors, where nodes communicate by sending each other messages that are encoded by the sender and decoded by the recipient. Now let's look at the nodes. Formats for encoding data. Programs usually work with data in at least two different representations. In memory, data is kept in objects, structs, lists, arrays, hash tables, trees, and so on. These data structures are optimized for efficient access and manipulation by the CPU, using pointers. When we want to write data to files or send it over the network, we have to encode it as some kind of self-contained sequence of bytes, for example, a JSON document. Since a pointer wouldn't make sense to any other process, this sequence of bytes representation looks quite different from the data structure that are normally used in memory. Thus, we need some kind of translation between two representations. The translation from the in-memory representation to a byte sequence is called encoding. It's also known as serialization or marshalling, and then the reverse is called decoding, or it's also called parsing, deserialization, and unmarshalling. Language-specific formats. These encoding libraries are very convenient because they allow in-memory objects to be saved and restored with minimal additional code. However, they have a number of deep problems. The encoding is often tied to a particular programming language, and reading the data in any other language is very difficult. If you store or transmit data in such an encoding, you are committing yourself to your current programming language for potentially a very long time and precluding integrating your systems with those of other organizations which may use different languages. In order to restore data in same object types, the decoding process needs to be able to instantiate arbitrary classes. This is frequently a source of security problems. For example, if an attacker can get your application to decode an arbitrary byte sequence, they can instantiate arbitrary classes, which in turn often allows them to do terrible things such as remotely executing arbitrary code. Versioning data is often an afterthought in these libraries, As they are intended for quick and easy encoding of data, they often neglect the inconvenient problem of forward and backward compatibility. Efficiency, CPU time taken to encode or decode, and the size of encoded structure is also often an afterthought. For example, Java's built-in serialization is notorious for its bad performance and bloated encoding. Now let's look at the writer and reader schema. With Avro, when an application wants to encode some data, to write it to a file or database, or to send it over the network, it encodes the data using whatever version of the schema it knows about. For example, that schema may be compiled into an application. This is known as writer schema. When an application wants to decode some data, that is, it reads from a file or database and receive it from the network, etc., it is expected that the data to be in some schema, which is known as the reader schema. That is the schema the application code is relying on. Code may have to be generated from the schema during the application's build process. With Avro, forward compatibility means that you have a new version of the schema as writer and old version of the schema as reader. Conversely, backward compatibility means you can have a new version of the schema as reader and old version as a writer. Let me repeat this point. With Avro, forward compatibility means that you have a new version of the schema as writer and old version of the schema as reader. Conversely, backward compatibility means that you have a new version of the schema as reader and old version as writer. Now, let's look at the merits of schemas. As we saw, protocol buffers, Thrift, and Avro all use a schema to describe a binary encoded format. Their schema languages are much simpler than XML schema or JSON schema, which support much more detailed validation rules. For example, the string value of this field must match this regular expression, or the integer value of this field must be between 0 and 100. As protocol buffers, Thrift and Avro are simpler to implement and simpler to use, they have grown to support a wide range of programming languages. Let's look at binary encodings based on schemas. Although textual data formats such as JSON, XML, CSV are widespread, binary encodings based on schemas are also a viable option. They have a number of nice properties. They can be much more compact than the various binary JSON variants, since they can omit fields names from the encoded data. The schema is a valuable form of documentation, and because the schema is required for a decoding, you can be sure that it is up to date, whereas manually maintained documentation may diverge from reality. Keeping a database of schemas allow you to check forward and backward compatibility of schema changes before anything is deployed. For users of statically typed programming languages, the ability to generate code from the schema is useful since it enables type checking at compile time. Models of data flow. The chapter discusses most common ways of how data flows between processes. The first is via databases, which means data flow through databases. Second is via service calls, that is data flow through services like REST and RPC. And third is via asynchronous message passing, aka message passing data flow. So to summarize, it's databases, service calls, and asynchronous message passing. Data flow through databases. In a database, the process that writes to the database encodes the data, and the process that reads from the database decodes the data. There may be a single process accessing the database, in which case the reader is simply a later version of the same process. In that case, you can think of storing something in the database as sending a message to your future self. Backward compatibility is clearly necessary here, otherwise your future self won't be able to decode what you previously wrote. This means that a value in the database may be written by a newer version of the code and subsequently read by an older version of the code that is still running. Thus, forward compatibility is often required for databases. However, there is an additional snag. Say you can add a field to a record schema, and the newer code writes a value for that new field to the database. Subsequently, an older version of the code, which doesn't know yet about the new field, reads the record, updates it, writes it back. In this situation, the desired behavior is usually for the old code to keep the new field intact, even though it couldn't be interpreted. Different values at different times. A database generally allows any value to be updated at any time. This means that within a single database, you may have some values that are written 5 milliseconds ago and some values that were written 5 years ago. When you deploy a new version of your application, of a server-side application at least, you may entirely replace the old version with a new version within a few minutes. The same is not true for database contents. The 5-year-old data will still be there, in the original encoding unless you have explicitly rewritten it since then. This observation is sometimes summed up as data outlives code. Data flow through services, for example, REST and RPC. When you have processes that needs to communicate over a network, there are a few different ways of arranging that communication. The most common arrangement is to have two roles, clients and servers. The servers expose an API over the network, and the clients can connect to that server to make the request to the API. The API exposed by the server is called a service. The web works this way. Clients, that is web browsers, make requests to web servers, making GET requests to download HTML, CSS, JavaScript images, etc., and making POST requests to submit data to the servers. The API consists of a standardized set of protocols and data formats, for example, HTTP, URLs, SSLs, TLS, HTML, etc. Because web browsers, web servers, and websites authors mostly agree on these standards, you can use any web browser to access any website, at least in theory. Let's look at web services. When HTTP is used as an underlying protocol for talking to the service, is called a web service. This is perhaps slightly a misnomer, because web services are not only used on web, but in general, several different contexts. For example, a client application running on a user's device making requests to a service over HTTP. This request typically go over the public internet. Example would be a native app on a mobile application or JavaScript web app using Ajax. One service making request to another service owned by the same organization, often located within the same data center as part of the service-oriented or microservices architecture. Software that supports this kind of use case is sometimes called middleware. One service making requests to service owned by a different organization, usually via the internet. This is used for data exchange between different organizations' backend systems. This category includes public API provided by online services such as credit card processing systems or OAuth for shared access to users' data. Asynchronous message passing systems, which are somewhere between RPC and databases. They are similar to RPC in that a client's request, usually a message, is delivered to another process with low latency. They are similar to databases in that message is not sent via direct network connection but goes via an intermediary called message broker, also called a message queue or message-oriented middleware, which stores the message temporarily. Using a message broker has several advantages compared to direct RPC. It can act as a buffer if the recipient is unavailable or overloaded, and thus improve system's reliability. It can automatically de-deliver the messages to a process that has crashed, and thus prevent messages from being lost. It avoids the sender needing to know the IP address and port number of the recipient, which is particularly useful in cloud deployment where virtual machines often come and go. It allows one message to be sent to several different recipients. It logically decouples the sender from the recipient. Thus, the sender just publishes the messages and doesn't care who consumes them. In the past, the landscape of message brokers was dominated by commercial enterprise software from companies such as TIBCO, IBM WebSphere, WebMethods. More recently, open source implementations such as RabbitMQ, ActiveMQ, Hornet, NATS, Apache Kafka have become popular. The detailed delivery semantics vary by implementation and configuration, but in general, message brokers are used as follows. One process sends a message to a named queue or a topic, and the broker ensures that the message is delivered to one or more consumers or subscribers to that queue or topic. There may be many producers and many consumers on the same topic. A topic provides only one-way data flow. However, a consumer may itself publish the message to another topic. Message brokers typically don't enforce any particular data model. A message is just a sequence of bytes with some metadata, so you can use any encoding format. If the encoding is backward and forward compatible, you have the greatest flexibility to change publishers and consumers independently and deploy them in any order. This concludes Chapter 4 notes. Hope this was useful. A nice time. Like and subscribe for more such content.